Thank you for tuning to my talk. I'm Ahmed Saeed, a postdoc at MIT, and this talk is about my work on Annulus, a dual congestion control loop scheme for data center and WAN traffic aggregates. This work was done in collaboration with my colleagues at MIT, AT&T, Sambanova, Intel, Georgia Tech, MPI, and Google. Let me start by providing some context. Cloud service providers are investing in high-capacity WANs to connect their data centers. For example, this picture shows some of the links comprising Google's WAN. The dates on the links show how rapidly the network has been growing. The growth in the infrastructure is motivated by the exponential growth in traffic demand. This figure shows one of the results reported by Google in the B4 paper a couple of years ago. The figure shows that WAN traffic demand increased by 100x over the period of 5 years. To adapt to this growth, it is now common for modern WAN links to have similar capacity to intra-data center links. So what does that imply? It implies that it's now typical in a data center to have the same rack or even the same machine sending high bandwidth data center traffic as well as high bandwidth WAN traffic. The WAN traffic we're considering here is not user-facing traffic that's bottlenecked somewhere in a wireless network or near the user. Rather, these are high bandwidth flows carrying large volumes of data. Think data backup across data centers. The congestion control algorithm used by a flow is determined by the sender using a flag that is based on the destination of the flow. WAN traffic uses WAN congestion control algorithms, and data center traffic uses data center congestion control algorithms. For the past decade, we've been developing WAN congestion control and data center congestion control separately. We've been doing this for good reasons, considering the differences between the two networks. On one side, data center networks have shorter RTTs and shallow buffers. They introduce the unique set of challenges like incast. Also, they offer homogeneity and provide the operator with full control over all network elements. This provides flexibility in deploying and experimenting with new algorithms. Significant progress has been made starting from DC-TCP to DC-QCN and Timely, and more recently HPCC and Swift. On the other hand, WANs have long RTT and high bandwidth demand. They have a mix of deep and shallow buffers. And aside from private WANs, deployment of new WAN congestion control algorithms have to take into account the heterogeneity of WANs, including competing with legacy congestion control algorithms. Recent proposals for WAN congestion control include VVR, PCC, COPA, and Nimbus. In this talk, we're concerned with bottlenecks shared between WAN and data center traffic, given that each type of traffic is using its own congestion control algorithm. In order to explore the interaction between data center and WAN traffic, we looked at traces collected from some of Google's clusters. We correlate the behavior of WAN and data center traffic in the data collected. The data I'm showing now is from one such cluster collected over the period of 2 days. The top figure shows the total throughput of WAN traffic exiting the cluster. The bottom figure shows the median, the 95th percentile, and the 99th percentile latency of all traffic in the cluster. The highlighted areas show that as WAN demand increases, the tail latency of data center traffic more than doubles. We also examined the drop rate at Tor switches. Tor switches are the first point of oversubscription in networks that we've studied and are the location of most of the drops. We see that the drop rate trends also follow WAN demand. This shows that WAN demand significantly impacts and degrades the performance of data center traffic. This behavior is consistent across different clusters and across different time periods. For the rest of the talk, I will explain in detail the reason behind this behavior and how we can remedy the performance impairments resulting from it. I will start with the punchline of our findings, which is that WAN traffic reaction to congestion is too slow compared to the fast dynamics of data center traffic. This statement might seem obvious, but some of its implications are subtle and result in performance degradation for both WAN and data center traffic. In order to better understand that statement, let's look at the timescales of operation of WAN and data center traffic. A typical WAN RTT is in the order of tens of milliseconds. On the other hand, data center RTTs are in the order of microseconds. When congestion happens, data center traffic detects it, reacts to it, and pretty much resolves it all before WAN traffic is even aware that there is a problem. In other words, WAN flows will take thousands of data center RTTs to detect congestion, leaving the full burden of congestion control to the data center traffic. I will illustrate this problem with an example from our simulation. In this simulation, data center traffic shares a bottleneck with WAN traffic, where the ratio between data center and WAN demand is 5:1. The top figure shows the number of bytes in flight, with data center traffic in blue and WAN traffic in black. The bottom figure shows the queue size at the bottleneck. We start by having total demand lower than the capacity of the bottleneck, thus having an empty queue. Then we increase the demand of data center traffic. Quickly, a queue starts to build up at the bottleneck and packets start to drop. Data center congestion control detects the congestion event and starts to back off, draining the queue. Notice that WAN behavior is unchanged. A WAN RTT later, we see the first WAN reaction, which happens after data center has already shouldered the full burden of handling congestion. Note that because of the slow reaction of WAN flows, the queue is never completely drained and data center traffic keeps observing large latency. Ideally, we would want WAN traffic to react to congestion and drain the queue faster. This illustrates how the behavior of WAN traffic degrades the performance of data center traffic. However, when data center traffic and WAN traffic compete in current settings, no one wins. To understand why WAN suffers, let's consider WAN buffer requirements. The rule of thumb of buffer sizing for cubic traffic is to allow a BDP of buffer per WAN flow. This means that short buffers like in data center switches can be problematic. Better algorithms like VBR or ECM-based schemes can have a smaller buffer requirement. However, this small requirement is under the assumption that the available bandwidth is stable. Data center traffic breaks this assumption. In particular, the bandwidth demand of data center traffic changes at data center RTT timescale. This means that the bandwidth available to a WAN flow changes hundreds of times within a single WAN RTT. This means that WAN traffic will suffer from excessive loss due to the lack of buffering and the rapid changes in available bandwidth at the bottleneck. To summarize our findings, WAN RTT timescale is orders of magnitude larger than the timescale of data center dynamics, which makes the data center traffic react solely to congestion, suffering all the throughput degradation. It also means that WAN can't accurately estimate the available bandwidth at the bottleneck. In other words, this difference in timescales of operation creates noise for WAN traffic. This noise can usually be weathered by having enough buffer at the switch to absorb overestimations by the sender. Those overestimations by the sender is what maintains high utilization. However, data center switches have very limited buffering. This means that any overestimations by the sender lead to excessive drops and long queues. And overall, this limited buffering leads to low utilization of the network. A natural approach to try to address this issue is to isolate the two types of traffic at the switch, dedicating buffer space to the different types of traffic. Aside from the waste of dedicating an already scarce resource, isolation is not a panacea. While it can help improve the performance of data center traffic, it does not solve the problems faced by WAN traffic. And this is for two reasons. First, there simply isn't enough buffer space at the data center switch to absorb a WAN BDP. Recall that we're concerned with high bandwidth WAN flows, capable of utilizing terabits per second of capacity in aggregate. This means that the WAN traffic can consume the whole memory of a shallow buffer switch. In other words, isolation does not address the problem of WAN traffic needing more buffer space. This is made worse by the fact that WAN traffic will still share the bandwidth with data center traffic, even if they're not sharing the buffer space. In other words, the available bandwidth to WAN traffic can change hundreds of times within a single WAN RTT. This exacerbates the issue of packet dropping caused by the lack of buffering. To better illustrate this problem, please take a look at this figure. This figure is from our simulations. It shows the normalized tail latency of data center traffic and the normalized average WAN throughput. It shows the ideal performance and the performance when both types of traffic are isolated at the switch. The data center traffic can achieve near ideal performance when isolated. However, WAN throughput suffers. You can find the details of the simulation in the paper. Now I'll introduce our scheme, Annulus, which achieves near ideal performance for both types of traffic. Our work on Annulus attempts to answer two questions. The first question is, how do we handle this new type of bottlenecks where data center traffic and WAN traffic compete? The second question is, how do we answer the first question while still efficiently handling all other types of bottlenecks? To answer the first question, we have to look at the root cause of performance impairments when WAN traffic and data center traffic compete. That is, the slow reaction of WAN traffic. Our main idea for an answer is to reduce WAN feedback delay, improving its reaction time to congestion. However, there are several ways to cut WAN feedback delay. One approach is to terminate and split connections at the interface between the data center network and the WAN. This changes the topology we have been considering. We add middle boxes at the interface between the data center network and the WAN. The middle boxes terminate the connections and manage congestion control for their respective segments of the path. This allows us to use data center congestion control for the data center segments of the path and WAN congestion control for the WAN segments of the path. This allows congestion control algorithms handling the data center segments of the path to react at data center timescale, thus resolving our problem. However, deploying these middle boxes incurs significant hardware costs and requires rethinking the topology of data center networks. Another approach is to allow the bottleneck to generate a direct signal to the sender when it faces congestion. This requires support from data center switches to generate and route such signals, and this is the approach we follow. The remaining question is how to handle bottlenecks that generate the direct signal, as well as bottlenecks that do not generate the signal. Annulus answers this question by relying on a dual control loop scheme. The first control loop addresses traditional types of congestion by relying on existing congestion control algorithms. In other words, when congestion control is used for WAN flows as the first control loop, and data center congestion control is used for data center flows as the first control loop. Annulus adds a second control loop that we call the near source control loop, which reacts to congestion at bottlenecks shared between WAN and data center traffic. Specifically, when congestion occurs at such bottlenecks, a switch generates an explicit and direct message that is routed to the sender, and the near source control loop reacts to it. Annulus fits in current stacks as follows. Current stacks already have congestion control algorithms that annotate packets with pacing rate based on some congestion signal piggybacked on acknowledgements. Annulus leverages those existing congestion control algorithms as its first control loop. It also adds a near source control loop which reacts to explicit notifications from the near source congested switches. And then it annotates packets with another pacing rate that's based on the near source control loop calculation. The rate limiter applies the minimum pacing rate, thus reacting to the most congested bottleneck. Now I'll discuss some of the details of the near source control loop. On queue buildup, a data center switch generates a direct congestion notification message that is routed to the sender. The message indicates the problematic flow that's causing congestion, as well as the extent of congestion at the bottleneck. The sender modulates the transmission rate of the problematic flow based on the congestion level at the bottleneck. Realizing the second control loop poses a couple of challenges. The first challenge is how to implement the direct signal in modern data center switches. The second challenge is how to define the interaction between the two control loops. I'm going to focus on the first challenge in the talk, and you can find the details of the second challenge in the paper. To implement the direct signal, we leverage the QCN standard, which is already implemented in several data center switches deployed in production. The QCN standard defines a purely hardware-based congestion control scheme that operates at layer 2. QCN enables switches, sample incoming packets, and on congestion, forward the congestion notification message to the sender of the sampled packet. The main challenge of leveraging QCN in modern switches is that QCN is an L2 protocol, while data center networks are L3 routed, and our design of Annulus is L4. To handle the problem of routing L2 packets, we leverage a feature in modern switches called L2 learning. L2 learning enables the routing of L2 packets in L3 networks, leveraging a dedicated memory for such function. This memory is populated by looking at the L2 addresses and the previous hop of all packets flowing through the switch. We also do not implement any of QCN's feature in hardware at the NIC. Rather, we allow the NIC to pass QCN messages from the hardware to our software stack where the near source control loop reacts to it. Our algorithm for the near source control loop follows the same basic rules of the QCN algorithm, which you can find in the paper. Now I'll present our evaluation of Annulus. Annulus test bed is comprised of 3 racks, 2 racks in the same data center and 1 connected to them through WAN. WAN latency is 8 milliseconds and LAN latency is in the order of tens of microseconds. We use 1 rack as a sender and the 2 other racks as receivers. To generate load, we use an RPC load generator where a machine in the sender rack sends traffic to all machines in the other 2 racks. The ratio between data center to WAN traffic is 5:1, and we use DCTCP and BBR as the end-to-end congestion control loops. We start by looking at the performance of data center traffic. This figure shows the 99th percentile flow completion time for data center traffic at different aggregate loads. It compares the case when Annulus is used and the other case where BBR and DCTCP are used by themselves for their respective types of traffic. Annulus reduces RPC latency by 40% even at 50% load. Next, we take a look at the behavior of WAN traffic. This is a time series of the number of packets in flight comparing when Annulus is used and when BBR is used by itself. Annulus maintains either 1 or 2 segments of 64 kilobytes in flight at all times. This behavior is due to its fast reaction, which allows it to adapt quickly to any changes in buffer size at the bottleneck switch. BBR's reliance on a delayed signal leads to a more bursty behavior, leading to packet loss and reduced utilization. In particular, we compare the bottleneck utilization when Annulus is used and when BBR and DCTCP are used by themselves. We find that Annulus improves bottleneck utilization by up to 5%. In conclusion, in this work, we identified a new problem in data center congestion control which arises when high bandwidth WAN traffic competes with data center traffic, and we introduced a new congestion control scheme to handle the problem. Annulus makes the case for developing better direct signals that reduce the reaction time and improve the performance of WAN traffic when handling congestion inside the data center network. We also believe that Annulus should motivate multi-control loop congestion control algorithms to handle scenarios where a flow goes through significantly different types of bottlenecks. Thank you, and I'm looking forward to your questions.